So let's take a look at assignment 5, kind of make a couple opening comments about the whole thing. It's really about mostly about energy and work, right? And then we will dive in and actually work some specific problems. I ever got the equation sheet in the email?
Yes, sir.
Okay, so that's the equation sheet you'll have all year. All the equations for energy are on there. Energy is a preferred way to work a lot of problems in physics if you possibly can work it using energy. What is one major advantage to using energy? Over using kinematics and forces, F equals ma, why is energy better?
Efficient. Well, energy doesn't change. It's always there.
Okay, energy is constant. It's not created or destroyed, as long as you can account for all the pieces of it everywhere. There's another major advantage. The major advantage around energy is that it's a scalar, not a vector. It doesn't have a direction. And so whenever something's accelerating, you have to ask yourself, okay, which direction is it accelerating in? Is the direction of acceleration changing? So, for example, there was a problem that we worked previously, and in that problem, there was something going in a circle. It was up here at the top, and it went down here, and like this angle was like 62 degrees, if you remember this from last one, homework set 4. And I actually worked it using energy. The reason is because at every single different point on the outside, as this rock was spinning in a circle, it had a different direction for the acceleration. It was not the same direction. All right, and these equations that we have become accustomed to using that might look like this for that's a plus, sorry, for acceleration or such. These kinematics equations are all based on a constant A that doesn't change. So if A changes, can't do it. All right, so we like energy in physics because energy is elegant. Energy is completely abstract. I don't even know what the heck energy really is. I don't. Okay, and that's true. Most physicists, if you try and lock them down, what is the complete definition of energy in all situations? That's like ridiculously hard to do. What I can tell you is I can watch energy transfer. I can watch it go from one form to another. I can watch it go from one object to another. And I can measure those things if we're very careful. It's very hard to say how much energy is in something. That's ridiculous because you got to look at all the atoms. You got to look at all the matter. You'd have to look at everything that's there, and to capture that whole picture is very challenging. Okay, it would involve all the forces that are interacting between all the particles that we're made of. And so rather than doing that with energy, what we do is we look at energy transferring, energy changing. Okay, and that's quick and easy to do. We primarily concern ourselves with types of energy. Okay, we look at certain types of potential energy, and we look at kinetic energy. We also discuss energy as a method of storage. Okay, I may even give you guys a little bit of reading, I get to my ninth graders, on how energy is storage. Okay, so where are you storing your energy? And if it is like, for instance, gravitational potential energy, how do you have gravitational potential energy? How do you make it bigger?
Go higher.
You go higher, okay? Why is that? Why is it that going higher gives you more gravitational potential energy? You are further away from the ground. Why does it give you more potential energy?
Like more time to accelerate.
If you were to drop, that's one way to answer the question, Nathan. If you were to let go of something from a higher height, okay, then it would have more time to accelerate. It could go faster before it reaches the ground, and when it hits, it would have more kinetic energy. So surely it had more potential. What's another reason, another reasoning as to why if you lift something higher, it has more potential energy with respect to gravity, where our reference point, say, is the ground, the floor. That's what we're going to say it has zero potential.
Chance to fall.
That's the same thing you just said a minute ago. Longer to fall, longer you accelerate, more chance to fall. Same line of reasoning. It's another line of reasoning.
There's a height.
There is a height in how to calculate energy. It is mass, right, times g, 9.8 on Earth, times the height. This is typically how we calculate potential energy to gravity. Here's another reason why. When you lifted it up, you actually had to exert energy yourself to lift it. Okay? If something's heavy and you're pushing it higher and higher, you get a little tired. And so that energy that you exerted to lift it up, it went somewhere. And some of it was stored actually in the gravitational field between, let's say I'm lifting up one of these empty bottles over here. I lift up an empty bottle into the air. Okay, so here's the ground, and he doesn't want his bottle lifted. Okay, and here's some kind of bottle, and I lift it up a certain height h, right? The work I did is stored in the gravitational field between the bottle and the earth. Okay, those two objects are actually holding the energy in the field between them. And if I let it go, then the bottle will fall, and actually the earth will also fall. We can't calculate the minuscule movement of the earth. Normally, actually arguing the earth would move up. I'm not arguing that. But the earth sort of does move up because it's being pulled up. Okay, but I bet somewhere on the other side of the earth, someone else just jumped off their bed or something and probably pulled it the same way, the same amount the other way. And the earth's really fat. I mean, enormously fat compared to a bottle. So while the earth is being pulled up and the bottle's being pulled down, the bottle moves down pretty much. The earth doesn't really move. Okay.
It does.
Theoretically, if it was the only object moving near the earth would actually shift toward it. Okay, and maybe the width of an atom. Okay, a very, very small amount because the earth's mass is so great. It doesn't accelerate greatly. Okay, but if there was something that was more massive that was falling toward the earth, let's say the moon fell toward the earth, then certainly what would happen is that the earth and the moon would fall toward each other. Okay, because the earth would have a significant gravitational effect, and actually it does have a significant gravitational effect even today. Okay, if you look at the moon and the earth spinning about each other, what effect does the moon have on the earth today? Tides. If you go down to the ocean, there's high tide and low tide. Okay, because water is forced down toward the equator and bulges when the moon is overhead. Okay, and then when the moon is not overhead and it's far away from that position, then you have a low tide. Because there's water that's kind of missing because it's bulging wherever the moon is. So as a result, gravitation potential energy can increase because as longer to fall, as Nathan said, also because you're pushing and you're giving energy to get it up there. Okay, that's potential energy due to gravity. It's based on the height, as you recognize. This is the key factor. The other two are pretty much like constant things. It's the height that's changing. Okay, let's do another potential energy at the same time here. Okay, elastic potential energy. Okay, now this is going to be a similar idea in that it's going to be based on position. Okay, now when I say elastic potential energy, I'm talking about what kind of stuff is elastic. For Van, good. What else? Okay, I have some toys on my desk that could be elastic. Specifically, we usually use springs. Okay, a spring has a certain elasticity, right? And as you all know from springs, some springs are really tiny, like say the ones in your mechanical pencils. Some springs are enormous, like the ones that they use for shock absorbers on big trucks and that kind of thing. Okay, so you can get springs that are very stiff, like the ones on trucks or the ones that lift your garage doors at home. Okay, or you can get springs that are not stiff, easy to move, with the ones in your mechanical pencils. The reason that understanding springs is really important is that even interactions between atoms sometimes behave like springs. Okay, and when you model interactions even on a very large scale, like galaxies and that kind of thing, certain things will behave in a spring-like way. Even things that are super tiny in quantum mechanics, like an electron in an atom going around in its ground state, will sometimes be modeled using what's called simple harmonic motion, which is the motion of something bobbing up and down on a spring. Okay. One other thing that it turns out that obeys the same laws of motion, that's not elastic, which is kind of neat, is a child on a swing set. Swinging back and forth is kind of, you go up and down, up and down. You keep on stopping and turning around at the edges. You go really fast in the middle on a swing set. And it turns out it's just like an object that's bobbing up and down on a spring over and over and over and over. It's turning around at the top, it's turning around at the bottom, an object on a spring, and it goes quick in the center. So all those things obey the same laws of motion. And so when I say elastic potential energy here, we're going to talk about a spring usually, but it's going to be a very global thing. You almost got it. That might go through a lot of other areas of physics we're going to see, from galactic things to subatomic things, okay? So 1/2, and then I'm going to write out words, and then I'll put symbols underneath, okay? And here you multiply times the spring, constant, okay? And for the spring constant, we give it the symbol K, right? And then you're going to multiply times, it's actually lowercase k, sorry. So 1/2 K, and then we're going to multiply it times, hang on, displace. Maybe I shouldn't do it this way, hang on. Brown just thought it was a slightly better way. You don't have to erase what you have in your paper. But I can't do it this way because of constraints of space and such. I apologize. Let me just write the equation first. K x squared. And now let me say underneath it what K and X are. Okay, so K is my spring constant. And X is my, you okay, Johnson?
Yeah. Okay.
Great. It's my displacement from equilibrium. All right. And so if I have a spring, and I probably ought to get one, what I want to emphasize for us is I want to emphasize that both of these potential energies are dependent upon position. Potential energies are dependent on your position in a force field. In the case of gravity, it's a gravitational field. In the case of a spring, it's the spring's force pulling or pushing on you, okay, that we're dependent on. But potential energies are based on your position in a field, okay, a force. Right? So you had to move something relative to a force. Those are two of the three main types of energy we will use most often. There's an equation for a third type, and you should know what it is. What is the equation for kinetic energy? Squared. So it's mass times velocity squared over 2. And when I say velocity, I'm very loosely saying velocity. It could just be the speed at that moment in time, because energy is not a vector. Energy is a scalar. And so I don't have any direction on the energy. So I don't have to actually use the velocity and worry about, oh no, is this supposed to be a negative 3 meters per second or 3 meters per second? It doesn't matter. You're going to square it. Okay? And so we're just going to have mv squared over 2. And that's going to be kinetic energy. These three kinds of energy are going to surmise most of our problems that we're going to work in this class. Obviously, if you were working on a class where you were dealing with a whole lot of fluid dynamics, okay, so you wanted to work with things about boats and all sorts of other stuff, we have to worry a whole lot about energies associated with fluid dynamics and such. Water pressure and everything else, sure. And if we wanted to do a whole lot of things around solar energy, we probably have to talk about solar energy, right? And the energy equations associated with light and radiation and photon emission absorption, but we don't have to worry about any of that, okay? So this is pretty much what we're going to be working on in this course, because we're working on mechanics for now. We'll have other forms of energy as we get into electricity and magnetism in the spring, because we'll have forms of energy between electrons and protons, and forms of energy that magnets will utilize and such. So we'll have some more energy equations as the year goes on. Okay, let's keep rolling here a little bit. Let's talk about a transfer of energy. This is usually when we actually do see energy, and usually when we talk about energy is because it's transferring. So we're changing the energy of an object by moving it around or pushing it so it goes faster or slower. or we're actually transferring energy to another object because it bumped into something. And that's work. Transfer of energy, when I use those words, what I'm talking about is I'm talking about the physics word work. Now, this is actually a really dangerous word because the word work is used in the English language in lots of ways. You go work out. This morning I got up, I got dressed, and I went to work. And so we use the word work in a lot of different contexts in the English language. But in physics, we're pretty much locking it into an energy transfer. Okay? So let me say one more thing up here at the top. I said in the beginning that energy is a form of storage. So specifically with potential energy to gravity, it's stored in the height. Or it's stored in the field. Okay, but it's stored in your position in the field. For elastic potential energy, it's stored in your displacement, your x, your position in regard to the spring's force. And the spring's
So is it the same like if you like move the springs like horizontally like this?
Correct, it's the same. Of course, horizontally on that table, there'll be friction. Okay, but if we had a frictionless track, which we do have an air track that blows air out of it, like an air hockey table, and things can float almost frictionlessly, yeah. We may. Okay. I've never actually even turned it on since I got here, but we will. The reason is because I have class sets of tracks of cars, but I only have one air track I'm aware of. And so because I only have, I've never had a class that's small enough to justify having the air track out for one lab group, but we might be able to do that here. So let's carry on here for the moment. Specifically with your kinetic energy, where the energy is stored is in the inertia. It's in the mass. The object in motion wants to stay in motion. That's where you store the energy. Okay, so it has a speed relative to you. So whatever velocity you're plugging in, that's the velocity you see it moving at. That isn't like the absolute answer for how fast it's going. Okay, for instance, how fast am I going?
0.
Oh, I'm going at 0 compared to you. I'm on the Earth. I don't know about you, but last time I checked, the Earth goes around every day. That's 25,000 miles if you're at the equator in 24 hours. That's over 1,000 miles an hour at the equator. That's pretty fast. And we're moving around the sun. We're moving around the sun, and we're moving at some ridiculous velocity. I think it's over 10 miles per second as we zip through space flying around the sun. Okay, that is not at 0. I'm at 0 relative to you. So kinetic energy is very much a how fast do I see you moving relative to me. Okay, and the energy is stored in the mass. And if you actually if you could find a way of weighing something as it flew by you at high speeds, according to Einstein, the faster it goes, the more massive it seems to be. To the point where its mass blows up toward infinity as you get close to the speed of light, which is another question for another course, not this one. Okay, so that's the basic introduction for energy. Let me talk a little more about work, and then we'll be done. Okay, so work. Work is typically defined as when you're transferring the energy, you're going to have to push or pull the object. Okay, so we're going to multiply force, and then we're going to multiply the force you apply to an object when you push it or pull it. And I want to look right at the point that you're pushing or pulling it, and I want to see what is the displacement of that object. How far did it move? And it has to be in a direction where, I'm going to just make a note here below, they have to be the same direction. Okay, force and the x are parallel. They have to be in the same direction. Okay, so I want to look at the displacement where you pushed it and how much of that displacement was in the direction of the force. I multiply those two things together, and this little bit of magic happens. And I use the word magic tongue-in-cheek, because why the heck would you multiply a force times a distance and get an energy? I have no idea. This is a mathematical backflip that we do in physics that always comes up with the units of joules. And what we figured out a long time ago, maybe 200 years ago, is that whenever things add up with joules, the number of joules never change, as long as you're really careful to look for them all. Maybe some of it escaped as sound when something hit. Maybe some of the joules got out as heat when something hit. But all the joules, if you can account for them all, it seems that they're all constant. Okay? And so that was not proven in physics until I want to say late 1800s, early 1900s. Someone came along. Her first name is escaping me. She was a famous mathematician. She was not a physicist, but she enjoyed the challenge, proving the laws of conservation, specifically conservation of energy in physics. Her last name was like Neuter or Netter. She's very, very famous. One of the best mathematicians ever lived, and you probably haven't heard of her because she was a woman, and that was not really popular 100, 200 years ago. And so I had to look up the year that she wrote her paper. Einstein called her the smartest person he ever met. Okay, so she proved the conservation laws for us, and that whenever these things multiply together, and you get joules, the total joules are constant. Okay, let's get into some problems. Okay, so looking at number one, Stan does 159 joules, lifting himself 0.3 meters. What is his mass? These kind of questions are easy. They're what I call plug and chug. Okay, they give you energy, right? They give you the height, 0.3 meters, the distance, the x, and they ask you what work is being done. Well, work is force times distance. The force in this case is going to be mg, right? Because that's his gravity, that's his weight that he lifted. And so I would just plug in 159 joules equals mg times his x, his distance, 0.3 meters, okay? And I would be able to figure out his mass, okay? What'd you get for his mass? Someone's done this, I'm sure. If not, please, if not, go ahead and divide 159 by 2.9. No, I'm trying to do it in my head. 2.94, yeah.
2.94.
Yeah, 159 divided by 2.94. Okay, 54.1 kilograms, okay? That is Stan's mass. Stan is a lightweight. He's a featherweight. I'm a full 120 kilos myself. Now, let me say one other thing. Do you note that the form of this equation right here is like mg and then the height that Stan lifted himself? So the work that Stan is doing, changing his energy, look at the form again for potential energy due to gravity. It's mgh. The work that Stan did, transferring energy, is being stored now as potential energy in Stan. So the two formulas are not just like similar, they're the same thing. You take the force of gravity, multiply it times the height, and that's the potential energy you have in that gravitational field, okay, that is stored there. So the work results in just his potential energy increasing. Let's go on and work something different over here. This is an interesting problem to look at because the two are not completely parallel. It says Mike pulls a sled across a level snow with a force of 242 newtons. If the sled moves a distance of 53.2 meters, which is pretty far, it's half a football field and a little more, how much work did Mike do? And so we want to look at the transfer of energy here. Let me get rid of this. Okay, and so let's look at this problem and kind of sketch it a little bit. So he is pulling at an angle of 42 degrees with a force of 242, was it? Yes. Yeah, 242 newtons, okay, in this direction. And then there is a displacement, right? And the displacement is going to go, I'm going to draw it like this, okay? And that was 53 thank you, meters. And so I want to multiply not all the 242. I want to find out how much of my 242 is in the same direction as my 53.2. Because that would be an adjacent vector, I want to use cosine. Okay, so right here, I just want to find that projection, that component of the 242. And so when I write out the formula for the work being done, I'm going to write, I have 242 newtons. And then I'm going to write cosine, so I want the adjacent side, of 42 degrees. And then I multiply that times 53.2 newtons, and I get the answer for the work.
Can you explain why you need cosine 42?
I do, because they have to be parallel. The blue arrow and the purple arrow are not parallel. And so what I did was I decomposed, or I broke up the force into two pieces. And one piece is going to the right, Nathan, and that is this one. This is 242 cosine theta. And this one is the opposite side. This is 242 sine theta. Okay, and so I took only one of those two components that is parallel to the motion, and that is the amount by which the energy of the sled was being changed. Okay. The other one was perhaps reducing friction because he was pulling upward, giving it less surface contact force, but it was not actually altering the energy of the sled. Okay. Sometimes the work formula that we have up here above, sometimes it's written like this: F. Sometimes they write it as absolute value of F times absolute value of X times cosine theta. For the same reason we just did, because you want the part that is of one vector that is parallel to the other vector. Okay. By the way, I'll just say one thing right now. I'm not going to prove it or do anything with it. That little dot in there does not mean multiplication in this case. It's a dot product. Okay. So this dot, and did you do dot products and cross products in calculus?
We just printed multivariate.
Wow, nice. Interesting. So this is a dot product, and all that means is that you do a certain mathematical calculation on it, and it does a couple of things. It only takes the part of F and X that are in the same direction, that is parallel, and it multiplies them together. And then it strips F, which is a vector, and it strips X, which is a vector. It strips them of their vector direction, and it leaves you an answer that's a scalar, a non-vector. Okay. We're going to see later in the year, you can also multiply force times the distance, and you can get a vector answer. All right. But you don't do it with a dot product where you multiply the parallel components. You do it with matrices. Do you guys do matrices at all in pre-cal?
We have matrices in
Algebra 2, like a 3x3 matrix or a 2x2 matrix. So if these are in 3 dimensions of space, like length, width, and height, you would do a 3x3 matrix times a 3x3 matrix. And you would do them in such a manner that you would do what's called a cross product, and you would have a resultant vector come out of it, and we will do that in like November, December. Yes, yes, and so it turns out you use the sine theta because you want the perpendicular components. Yes, okay. And so we'll spend more time working with those. Those are new to the formula sheet last year. I've never seen this in the formula sheet before. That was interesting to put them on there. I'll tell you the truth. I'm kind of baffled to put them on there, but I guess it is more of a math thing than a physics thing. All right, let's keep going here. I have 9:10, and so we have about 15 minutes. Most of these problems are this plug and chug. They're not that difficult. Okay, let me go down a little bit. Somehow I highlighted the entire page. That's really funny. Let's do number 4, just for the heck of it, because it's an elastic one, okay? And it's the first elastic one we're kind of bumping into here. So we have a certain spring, and it stretches 3.5 centimeters when it supports 0.79 kilograms. And it asks, if it can stretch this far, how far would it stretch with 10 kilograms on it instead? So 3.5, 7.9. So let's go ahead and take a look at this. This is number 4. Now, I'm going to convert this to meters, okay, just because I want to. I usually convert things to meters because meters are my default units, okay?
Like the answer is just
Well, then this is probably a wasted step here. Sorry, maybe you don't want to do this. That's fine. You can leave yours in centimeters. Let me take a look at this and figure out what's going on. So I have a spring, and my spring looks like this. And when I hang a 0.79 on it, it gets longer. It gets that much longer. Right? It gets this little tiny distance right here of 3.5 centimeters is how much it gets longer by. Okay, so just like we saw earlier, if this is equilibrium right here, then I can make a statement about the forces acting on it. I can say that I have mass times gravity, or the force of gravity going down, and going up, I must have the force of my spring. And those two must be in balance. Okay, I could say here that the mgh, by which the mass decreased, equals the 1/2 kx squared up. That would also be true. Okay, that is that the energy of the two is transferring back and forth. To do this problem, I am going to need to know the force of a spring, which I don't have that equation. I know, but I want to show you how you can find it from right here. Yeah, what is it, Johnson?
Oh, can we just do just,
A ratio.
yeah, just ratio.
Yes, you can, because the equation is linear. Let me show you why it's linear, though. This equation right here, x, in this equation right here, x is the variable. K is a constant, and 1/2 is a constant. So x is my variable. This is energy. Do you remember how energy is related to, how force is related in work, right? It's force times distance. Okay, so a little bit of calculus here. If you take the derivative of this formula, you get the force that is associated with the energy. Say it again. If you take the derivative of this formula with respect to x, it gives you the force that the energy is stored in. So what is the derivative of this with respect to x?
2x.
Kx. There's a 1/2 in front. Cancels the 2.
Oh,
So the 1/2 and the 2 balance out. You're left with kx. So it turns out the force for a spring is kx. Let's do it one more time. Here's gravity. Height is my variable here. If you differentiate this with respect to height, what do you get? If you differentiate this function, mass times gravity times height, with respect to height, you get mg. Sure enough, that's the force that's associated with the potential energy function. Okay, so the derivative of the energy function, the potential energy function, is the force. That is a relationship that should not surprise us because it's right here in the work. Right? If you differentiate this with respect to x, you get the f. Okay. Now, sometimes there's a sign thing that pops in here a little bit because you have to ask yourself, if the work is the energy transferred, then sometimes I'm the one giving the energy to a spring. So maybe the spring's energy, maybe my energy is negative. Maybe my work was negative because I gave up energy, but the spring gained energy. So you got to look at who's gaining and losing the energy. So we'll see a negative sign come into this at some point later. But let me just make a simple statement and say the derivative of the work, the derivative of the energy stored, the potential energy, is the force associated with that energy function.
Can I take a 10-second question? Your kids?
You can. I have 10 minutes.
How many weeks in a month?
Or 5.
How many would you say? Thank you. Okay.
On average, 4.33.
Love the physics person.
Why, what did this class say?
He comes in here on a regular basis and has to ask.
I know. Last year,
Yes. And he comes in here, he just likes, there's something about his style that likes to say, I'm not the only one that thinks you're stupid. Let me just show you. And I don't mean that in a condescending way, I don't, because I love Todd. He's awesome. Yes, but he regularly comes over here and goes, would you believe what this class just said to me? Would you believe what they just said to me? God, what are they raising these kids on these things?
Did they say like 3 or like 7 or like?
I have no idea what they said. Yeah. But it's kind of a trick question. Like you said, 4 or 5, because the answer is not singular, right? I mean, there's 30 days, 31 days, 28 days, 29 in leap year. But what are you talking about here, bud? All right. Let's carry on. I can't remember what we're doing. Oh, the force of a spring. The force of a spring is kx. So here's what I'm going to do in this problem. Here's why, Johnson, you can set it up as a ratio. I am going to set up that mg down equals kx up. Because the two forces are in equilibrium. They're equal and opposite, right? You don't need a negative sign in there. So if you did have a negative sign, I would call like the red one positive, the purple one negative. And the way I would actually write that, if I was to kind of do that maybe a little bit more official, I'd write it out like this first. The sum of the forces are 0. And then I would write the force of the spring minus the force of gravity is 0, right? And then I would plug in kx minus mg is 0. And then I would add 1 to the other side, right? And then I would end up, so I skipped these steps. I apologize. I probably should not have. Let's go ahead and plug in. We know 3 of the 4, and so we can figure out the 4th. I'm going to leave the 3.5 back in centimeters because you mentioned we wanted an answer in centimeters. So let's do that. My mass was 0.79. Gravity, we're using 9.8. I'm leaving off units because I'm trying to go fast. And my x was 3.5. I'm sure someone has k by now. We here have k. Bueller knows k. Yeah, Frank constant.
Ahead of the game like that. 9 times 9.8.
I got the same. So 2.12, and this would be in newtons per centimeter, okay? Because on top you have mass times gravity.
0.21.
Oh, I got it. Thank you. Okay, now I want to work the second part of the problem. The second part of the problem is, what if the mass was 10 kilos? What would be the stretch? So I'm going to plug into the exact same equation I have here, right? I have kx on one side, I have mg on the other. Now I know what k is, but I don't know m. Sorry, I don't know x. And so, sure, this is newtons per centimeter. X equals 10 kilos times 9.8, which of course is just 98. Okay, so
98 divided by 2.4.
yeah, invert times 98. We got 44.3. Yeah. Okay. So that is how many centimeters of stretch you would have with 10 kilos. Okay, which is a realistic amount. That's like 1.5 feet. That's not a crazy amount of stretch. Okay. And so that is how you do elastic type problems. Okay. Let me just skim really fast and see if there's something else that's like brutal that we should do. Let me just say that for number 6, 7, 8, you're going to find for 6, 7, and 8, you get about the same answer. What they're trying to show you is that all the work being done resulted in a change in KE of the train. So a train gets a big push, it goes really fast as a result. So they say, what is the work? And you get a number. It's like, say, 75 million joules. What is the kinetic energy of the train? 75 million joules. If it started from rest, what is its final kinetic energy? 75 million joules. And they just want you to see that the work is the energy. So don't be distressed if you get the same answer over and over, okay? Car hits a tree, doesn't move, and comes to rest. What is the change in kinetic energy of the car? That's too easy. I'm gonna leave that alone. You're gonna be fine. Let's do 13. 13 asks for what is the power of old Wayne. Wayne, there's a Wayne. You gotta get in touch with Wayne here, man. You gotta feel Wayne's pain. Yeah, Wayne's got pain. Now, Wayne's got power. Power is not energy. Do you know how power is related to energy? Power is the rate at which you do energy. So if two people who are the same size run up a staircase, same mass, run up a staircase and one runs up more quickly, we say the quicker person is more powerful. Not because they exerted more energy, they actually probably exerted the same energy running up the stairs, but one of them exerted the energy in a shorter period of time. They had a higher rate of energy transfer. Okay, and so as a result, they are more powerful. On the formula sheet for physics, it has power, and it has two equations for power typically. One is a derivative. It's a rate at which you're doing power. So this is how power is often written. It is the derivative with respect to time of your work. It's the rate at which you're working, the rate at which you're transferring energy. Okay. There's another form that has no calculus to it at all. It only works if the force is constant, right? And for that one, it turns out the units are the same. Why did I put a dot? Because I'm weird. I'm going to put equals. F dot V. This dot right here, once again, is a dot product. And what the dot product means is that you're going to have to be parallel. So I need only the parallel component of F and V for that formula to be true. We're not going to use the power very much. We will probably do it throughout the year, spend no more than 15 or 20 minutes discussing power. Power is usually about 1 or 2%, maybe 2% of the AP exam, and it's pretty straightforward and it shows up, so it's not something you spend a lot of time on. But let's just spend a minute here talking about Wayne's power. So let's look at the problem, and for this problem, Wayne is going to pull a sled. He's going to pull it at an angle. So what are we thinking right away?
Sine or cosine.
I'm going to need a sine or a cosine. Because I'm doing work, what do I need?
Same.
Cosine.
Okay.
Work has a cosine in it, okay? And so Wayne pulls a heavy sled along a path. Wayne pulls with a force of 91.9. So it turns out I don't actually care about that force right there. It looks like it might be extra information. That's just how much the sled weighs. That's not the force that Wayne exerted. So I want to stick to this 91.9. I want to stick to the 17.1 meters. I want to use the 30 degrees.
So it's not a net force, it's just a force of.
If it is a net force, then it gives you the net work. Let's say there was friction in a snowy path, and the friction was resisting it. I would take 91.9 cosine 30. I would subtract the friction, and I'd have a net force, and that would give me the net work. You could also figure out how much work is being done by just the frictional force, multiplying frictional force times distance, Kaya, and that's really useful for seeing how much heat is being generated between the snow and the sled, okay? That's what friction does, generates heat. So this is the only force I'm given, so this is the only force I'm finding work due to, okay? So so let's just jot down what we're going to do here. I can't remember what number we're on. This is number 13, okay? This is 13. We're going to feel powerful. And here's my formula, that work is equal to force, distance, okay, cosine theta. So let's find this work, and then we'll do the power. 91.9, I can't write today. 91.1, what was it? I'm forgetting already. 91.9, that's not what I wrote, so I'm very silly. 91.9, 17.1 meters, and cosine of 30 degrees, yes. Okay. Cosine 30 is like what, square root of 3 over 2? Yeah. So you multiply this out, and you find out the work that Wayne has done. If someone wants to do this.
I got 1,000.
61, yeah. Okay, I got the same thing. And 60 is better because we only have 3 sig figs in our stuff here. They don't grade for sig figs closely on AP Physics. But if you put a ridiculous number, if I put a decimal here and put 5 more numbers, I'd actually lose a point. Because they'd be like, okay, that's ridiculous. No one had 10 significant digits in that. You had 3, you had 3. If you give me 3 or 4 back, I'll go with you. More than that, you're insane, okay? So, okay, this is in joules. So we'll have to end with this one here because we're running out of time. And this, now when I want to find the power, there's no calculus here. I'm just going to take the work. Yeah, I'm going to divide it by the time, okay? So I'm going to take the 1360 joules. There's no calculus in any of this homework. Okay, the summer homework is specifically designed to be calc-free because it's just a review. Divided by the, if I remember, it was 2.1 seconds. Okay, and so I got 648. And the answer for the units here,
647.
yeah, hang on a second. Yeah, 648 watts, okay?